Hi everyone, my name is Shubham Sharma and I am from Kyushu Institute of Technology, Japan. The topic of my presentation is Engineering Stable Interfacial System for Oriented Floating Films of Donor-Acceptor Semiconducting Polymers. I would like to begin with organic electronics. What is organic electronics? It is a field of material science concerning the design, synthesis, characterization, and application of organic semiconductors. There are several advantages of organic electronics, like the devices made using the organic materials are much lighter, they are very flexible, they are very less expensive as compared to the inorganic counterpart. They are easy to process and they have low fabrication cost. There are several advantages like smart windows, RFID tags, flat panel display circuitry, flexible solar cells, electronic papers, etc. Organic electronic materials are constructed from organic, that is carbon-based small molecules or polymers using synthetic strategies developed in context of organic and polymer chemistry. Now, what is conducting polymer? So, conducting polymers are the materials, the polymers that conduct electricity. As we know that metals are conductors, semiconductors are somewhere between metals and insulators. The conductivity is between metals and insulator. And insulators are non-conductors, but we can make these conducting polymers and they can be tuned from metallic to insulating regime. And the most important aspect of these conducting polymers is that they can be processed into a solution. Now, a top part of conducting polymer is conjugated polymer. Organic macromolecules with backbone containing alternate double and single bond are conjugated polymers. That means they are conjugated. They have overlapping p orbital, which creates delocalized pi electrons. This results in interesting and useful optoelectronic properties. Here are some examples of conjugated polymers like polyacetylene, polyaniline, polythiophene, etc. So the conjugated polymers are quasi one-dimensional materials with extended pi conjugation, as you can see in the picture. They have a flat molecular structure, which helps us make a very thin device. They have inherent tendency of molecular self-assembly, and this helps in controlling the final optoelectronic properties. Now, we have to process these materials into thin films. So, what is thin film processing? Facile and large area thin film processing with pronounced carrier transport is highly desired for high performance organic device. Well, there are majorly two techniques, one for small molecules, which is thermal evaporation. That is, the material is evaporated in a thermal chamber at a very high vacuum, at a very high temperature, and they are deposited on the desired substrate. For the second one, that is for the conjugated polymers, we have several methods like spin coating, which is one of the highly used method in the whole world, spray coating, drop casting, doctor blading, inkjet printing, etc. Now, there's an intriguing issue that in these techniques, that is, what is the influence of the material, or the underlying material? For example, if we deposit one material and we want to deposit another material on the top of it, what happens to the underlying material? There is, in these techniques, there is a mechanical damage, there is a composition damage, and there is a solubility issue. So in order to rectify these issues, we have devised a new technique in our area that is called floating film transfer method. Now, what is floating film transfer method? So basically, we take a liquid substrate, and in this case, we have taken the blue color, as you can see in the picture, we have taken ethylene glycol. We can take water, we can take glycerol, etc. And we take polymer solution. In this case, we have taken the polymer solution in chloroform. And as you know that chloroform and ethylene glycol, water, and glycerol, etc., they don't mix together. they are immiscible. So what will happen? And we have used a slider to help the spreading of the polymer film in the single direction. We just take around 10 microliter of the polymer solution and we drop it on the liquid substrate, that is ethylene glycol in this case, on the top of the ethylene glycol. And because of the slider, it starts spreading in one direction. Now the question here is, why does it spread in a single, why does it spread? And why does it spread in a single direction? The spreading is because of the interfacial surface tension between the two liquids, and it, because of the slider, it helps the polymer film to orient, to flow in single direction. Now, because there is an expansion direction, and because of the ethylene glycol at the bottom, which is the lower liquid, it is providing a compressive force, as you can see in the picture on the right. It is providing a compressive force because of which the polymer domains can orient in one direction. So the advantages of this method, the floating film transfer method, is there is no need of sophisticated instrument, there is no material wastage, the fabrication, that is multi-layer fabrication, can be done, and there is molecular alignment. In this work, we have used the polymer DPP-TTT, as you can see in the picture, and we have used this polymer. It is a donor-acceptor type polymer, that is, it has a donor unit and an acceptor unit in the same, in conjugation, in the same polymer. Now, let's discuss the role of viscosity. What is the role of viscosity? So, for example, if we take a low viscosity upper liquid, that is the polymer solution, and highly viscous lower liquid, which is in this case is ethylene glycol. If the polymer solution has low viscosity, so during the spreading of polymer liquid, the hydraulic resistance of the low viscosity polymer solution is low, and thus the stress provided by highly viscous lower liquid, that is ethylene glycol, induces the spatial coordinates of the upper liquid, that is the polymer solution, to orient in perpendicular direction to its vector velocity, that is flow velocity. This is called unstable viscous system. Now let's take an example of highly viscous polymer solution, which in this case is 45 gram per liter. So, and we have taken the lower liquid as the same ethylene glycol. So now, when the upper liquid has higher viscosity as compared to the lower liquid, the local hydraulic resistance of the polymer solution is high and spreading is slow. The domains come closer to each other and they form closely packed, long-range ordered aggregates. And the orientation, the ordering is in the same direction as the flow. They will orient in the same direction as the flow, unlike the upper case, the above case. This is called a stable viscous system. So thus, in this work, we have engineered a stable viscous system for orienting the polymer, and thus we can utilize this engineering of the stable system in making organic field effect transistors. Now, after this, we have studied the UV visible absorption characteristics of the thin films in both the cases. So as you can see in the picture, when the film is 10 gram per liter, is fabricated using 10 gram per liter polymer solution, you can see that, as we discussed previously also, the orientation is in the perpendicular direction to the flow. And because of this, there is mixed coil and rod type structure. They have smaller size domains and loosely packed aggregates. In the other case, that is the 45 gram per liter polymer solution, where the polymer solution has a higher viscosity as compared to the lower liquid ethylene glycol, the orientation is in the same direction as the flow. This helps in getting extended rod-like aggregates with large size, and these aggregates are very closely packed. And also you can see that the dichroic ratio of 45 gram per liter is more than the 10 gram per liter, which shows that orientation is more in 45 gram per liter. Dr represents the orientation. So 45 gram per liter polymer solution have higher dichroic ratio. The other parameter which helps us understand orientation more is called 2D order parameter. So in 2D order parameter, if the value of 2D order parameter is 0, it means that there is no particular orientation. It is isotropic. There is no orientation. If the value of 2D order parameter is positive, it means that the orientation is in the same direction as flow. And if the value of 2D order parameter is negative, it means that the orientation is perpendicular direction to the flow. So we have taken a lot of different types of polymer solution with different viscosities and different subphase liquid, that is the lower liquid. And we have tested with a lot of liquids, the upper as well as the lower liquid. And we have come on this common conclusion that if the viscosity of the upper liquid, that is the polymer solution, is less than the lower liquid, that is the subphase liquid, in this case, in the previous slide I told you, which is the ethylene glycol, the orientation is perpendicular direction to the flow. And in the opposite case, when the viscosity of the polymer solution, the upper liquid, the polymer solution is more than the lower liquid, ethylene glycol, the orientation is in the same direction as the flow. So there is an enhanced molecular self-assembly after the orientation is reversed. Now, we have characterized these two types of different polymer solution and their film, and we have studied the anisotropic charge carrier transport, and we have fabricated organic field effect transistors. So you can see this is the transfer characteristic of the organic field effect transistor. Here we can clearly see that 45 gram per liter polymer solution based organic field effect transistor has much higher mobility as compared to the 10 gram per liter polymer solution based organic field effect transistor. This is because of long range ordered polymer solution in 45 gram per liter. They are long range ordered, they have extended backbone, extended conjugation, and they are very closely packed aggregates in the 45 gram per liter polymer solution. So this is a comparative table describing the mobilities of the two different types of polymer solutions. In 45 gram per liter, we have achieved a mobility of more than 12, around 12.4, 12.5 centimeters square per volt second, as compared to the 10 gram per liter polymer solution, where the mobility was around 2.5, 2.6. So the mobility in 45 gram per liter is much higher as compared to the counterpart. Also, another important parameter that we can understand here is the anisotropic charge carrier transport. The anisotropy in charge carrier transport is much higher in 45 gram per liter as compared to the 10 gram per liter polymer solution. So this mechanism, we have proven this mechanism by the electrical characteristics of organic field effect transistors in their parallel as well as perpendicular direction. So as a conclusion, I would like to say that we have shown that the reversal of orientation direction was accompanied by enhanced molecular self-assembly, and this synergy led to enhanced and facile charge carrier transport. This reversal in orientation provides closely packed molecular domains, which further enhances anisotropic charge carrier transport, resulting in one of the highest reported mobilities of this class of conjugated polymer in the world. Thank you.